Today we'll start the flexibility method analysis. So already we have discussed in last class what is flexibility and what is stiffness, and what is the flexibility matrix and what is the stiffness matrix. The flexibility matrix method of analysis is basically a consistent displacement method cast in matrix form. This method is basically a consistent displacement method, and that you have to analyze by matrix form. This method can be used for analysis of statically determinate as well as indeterminate structures. In this method, the basic unknowns are redundant forces. Hence, the analyst has to first identify the basic determinate structure and thereby identify the redundant forces. The number of redundant forces is equal to the degree of static indeterminacy. So in this method, what you have to do? So first you have to make the structure your determinate, and you have to identify the redundant forces. The redundant forces is equal to the degree of static indeterminacy. The displacements in the basic determinate structure are due to a given loading, and redundant forces are found and the consistency conditions are followed. So here you have to find out the displacement in the basic determinate structure are due to the given loading and also due to the redundant forces. The resulting simultaneous equations are solved to get the redundant forces. Then you have to solve the simultaneous equations. Then you can find out what are the redundant forces. Now this method is known as force method or flexibility method or also compatibility method. What is the procedure to solve using the flexibility method? In this method, the basic unknowns to be determined in the analysis are the redundant forces. Hence, the degree of static indeterminacy of the structure is identified first. So first you have to find out the degree of static indeterminacy, then you have to identify the redundant forces. Which force you have to take as a redundant forces. Then the coordinates number is assigned to each redundant force direction. Thus P1, P2, P3, Pn are the redundants at the coordinates 1, 2, 3, n respectively. If restraints to all the redundants are removed, the resulting structure is called the release structure or basic determinate structure. So first you have to find out the degree of static indeterminacy. Then you have to choose the redundant forces and you have to give along the coordinates the redundant forces. Then after restraints of all redundants, the resulting structures that will convert to the release structure or basic determinate structure. From the principle of superposition, the net displacement at any point in a statically determinate structure is the sum of the displacement in the basic determinate structure due to the applied load and the redundants. You have to find out what is the displacement due to the applied load, and you have to find out what is the displacement due to redundant force, and the sum is the net displacement at any point in a statically determinate structure. So this condition known as compatibility condition and may be expressed by the equations. So this is the total displacement and the displacement due to the applied load, and this is displacement due to the redundant forces. Similarly, at delta 2 and delta j and delta n. So where delta j is the displacement at a coordinate j in the statically determinate structure. Then delta jl is the displacement at a coordinate j in the release structure due to the applied loads. Delta jl is your displacement at a coordinate j in the release structure due to applied load. Then delta jr is the displacement at a coordinate j in the release structure due to the redundant forces. The displacement at coordinate j due to the redundant force, and this is the displacement at coordinate j due to the applied load, and this is the total displacement at coordinate j. Delta j is equal to delta jl plus delta jr. Similarly, here also delta 2 is equal to delta 12, delta 2r, and delta n is equal to delta nl plus delta nr. Here delta n is your displacement at a coordinate n in a statically determinate structure, and delta nl is your displacement at coordinate n due to the applied load, and delta nr is your displacement at a coordinate n in the release structure due to the redundant forces. This is your equation 1. equation 1 may be expressed in the matrix form. You can express this equation in the matrix form. So delta is equal to delta L plus delta R. So this is equation 2. So this is your column matrix, and this is also column matrix. Delta 1, delta is equal to delta 1, delta 2, delta 3, and delta n. Similarly, delta L is equal to delta 1L, delta 2L, delta JL, delta NL, column matrix, and delta 1R, delta 2R, delta JL, delta NR. This is column matrix. You know that is in flexibility matrix. So delta 1 is equal to this one, and delta 2 is equal to delta 2 1 P1 plus delta 2 to P2 plus delta 2 1 PL. What does it mean? So delta 1 means this is the displacement at 2 due to unit force at 1. Similarly, for n coordinate, delta n is equal to delta n1 P1, delta n2 P2 plus delta n PL. So putting the value of delta 1, delta 2, delta 3 in equation 1. Just to put this in equation 1. So the this equation 1, this one, then we'll put here in equation 1. So this becomes, after putting this one, so delta 1 is equal to delta 1L plus delta 11 P1 plus delta 12 P2 plus delta 1N PL. Delta 2 is equal to delta 2L and this one. Then delta n is equal to delta NL plus delta N1 P1, delta N2 P2 plus delta NN PL. Equation 3. So equation 3 may be written in the matrix form. You can rewrite this equation delta 1, delta 2 and delta n in the matrix form. So here delta 1, delta 2, delta n is your indicate this is delta, and this is your delta 1L, delta 2L, delta NL. So this is your delta L, and this is the flexibility matrix L into P. You can find out the redundant force P by taking delta minus delta L and the inverse of this one. This is your equation 5. You have to remember this equation. In the indeterminate structure, the final displacement delta are either 0 or non-value. This is the final displacement is either 0 or non-value. If the net displacement of the redundants are 0, then you can put delta 1, delta 2, delta 3, and delta n is equal to 0. This is your equation 5. So equation 5 becomes, and we'll put this one, delta 1, delta 2, delta 3, delta n is your 0. Here you have to put 0. So the equation 5 becomes P is equal to del minus 1. So this is your 0. So minus delta L. So the redundant force you can find out using this formula. So inverse of the flexibility matrix, inverse of the flexibility matrix into delta L. The solution for P from the above equation gives all the redundant forces. So the objective is you have to find out here the redundant force. Then after getting the redundant force, then using the equation of static, the bending moment and shear force may be calculated. So it may be noted that the force method is actually the method of consistent deformation expressed in a systematic manner through the use of matrices. This method is known as force method because the compatibility equations are divided by the superposition of two systems of forces, one applied load and the other redundant forces. That's why this is known as the force method, because the compatibility conditions equation are derived by the superposition of the two systems of forces. One is your load and another one is your redundant forces. So another reason of this method, the forces are treated as unknowns. So this method, you have to treat the forces as a unknown. The method is also known as flexibility method because the flexibility matrix has to be developed to establish the compatibility of displacement. So why this is called the flexibility method? Because here you are using the flexibility matrix to establish for the compatibility of the displacements. As the condition of compatibility of displacement is utilized in this method, it is also known as the compatibility method. You can say this is your compatibility method or flexibility method, or you can say force method. So, these are the different names of this method. Then these are the steps that you have to use for analysis of any statical indeterminate frame or beam. First, you have to find out the degree of static indeterminate. This is the first step. Then the second step is choose the redundant. Assign the coordinates 1, 2, 3, n to the redundant. If the degree of static indeterminacy is n, so you have to choose n redundant forces. Then you have to assign the coordinates 1, 2, 3, n. Then removing all the redundants, the structure becomes release structure. Determine the displacement delta L in coordinate direction due to the given loading. So you have to find out the displacement in the coordinate direction due to the given loading in the basic determinant or release structure. Then you have to find out the delta R, that is the displacement due to the redundant forces in the basic determinant structure or release structure. Then after getting the displacement due to the applied load, and this is the displacement due to the redundant force, then what you have to do? Determine the displacement delta, the displacement at the coordinate due to the redundant acting on the release structure. Then you have to compute the net displacement. So you know this is the formula, computing the net displacement delta is equal to delta L plus delta R. So delta L, this is due to the applied load, and this is the displacement due to the redundant forces. Then apply the condition of compatibility of displacement to compute the redundant force. Then if the net displacement is 0, then you have to put delta is equal to 0. So the equation becomes P is equal to delta inverse 1 minus delta L. Knowing the redundants, compute the internal member forces by using equation of statics. So after getting the redundant forces, then you can find out using the equation of statics what is the bending moment, shear force, everything that you can find out. Note, you have to remember, for assembling displacement deflection delta L in release structure and to assemble the flexibility matrix delta, use standard method known in structural analysis like conjugate beam method or unit load method. So using the conjugate beam method or unit load method, so you can find out the deflection or the displacement due to the L, the applied load, and also due to the redundant forces. So this is the question. Analyze the continuous beam shown in figure by flexibility method. Here you see this is the continuous beam, and the end is your fixed, and the B is your supported, and C is your supported. And the length of the beam is your 4 meter, and here 1.5 meter, 1.5 meter, having one concentrated load at the midpoint of the beam, and here having the uniform distributed load throughout the beam, 60 kilonewton by meter. So first you have to find out the degree of static indeterminacy. You know how to find out the degree of static indeterminacy. How many reaction component here? So because this is your fixed, so here the reaction component is your 3. Because this is the roller support, so here the reaction component is your 1, and here also the reaction component is your 1. So 3 plus 4 plus 5. The total reaction component is your 5. Then number of independent equation. Then number of independent equations of equilibrium is your 3. You know how many number of static equilibrium equation? 3 equations. So what is the degree of static indeterminacy? So 5 minus 3. The degree of static indeterminacy is equal to R minus 3. R is the number of reaction components minus the number of static equilibrium equations available. So the degree of static indeterminacy is equal to 5 minus 3 is equal to 2. Here you have to choose 2 redundant forces because the degree of static indeterminacy is equal to 2. So you have to choose 2 redundant forces. 2 redundant forces are to be released to make the beam statically determinate. So these are the different alternatives that you can release of the redundants. So you can release MA and MB because here there is your having the moment, and here also there is having the moment, but here the moment is your 0 because this is the simply supported end. So here moment 0, but here having moment, here also having moment. So after releasing these 2 moments, the structure becomes the determinant. Or also you can release the moment at A and reaction at B. So you can also release the moment at A and the reaction at B. You have to release this reaction. Then the structure becomes the determinant. These are the different alternatives. Or you can also release RB and RC, reaction at B and reaction at C. Then the structure becomes the determinant. Any 2 forces, any 2 redundant forces you have to release, then the structure becomes the determinant or released structure. These are the different options. So here in this case, in this question, we'll release the moment at A and we'll release the moment at B. Here we will release the moment. So after releasing this moment, so this becomes the simply supported, and here also after releasing the moment, so this becomes the simply supported. Then this is your converted to the determinate structure. In this question, the moments at A and B considered as redundants, So select MA and MB as redundant forces. We will choose MA and MB as a redundant forces. We will choose MA one redundant force and MB one redundant force, two redundant forces. After release of these two redundant forces, then the structure becomes the determinate. The release structures comprise two independent simply supported beams. So after releasing these two moments, so the structure becomes this one. The release structure comprises two independent simply supported beams, AB and BC, AB one beam and BC another beam, as shown in figure. This is the figure, release beam. This is the determinate structure, or this is the release beam or determinate beam. The coordinates selected as shown in figure. So you have to select the coordinate. So here you have to choose, because you are taking the moment MA as a redundant force and the moment MB as a redundant force. So you have to choose the coordinate, that is the rotation. Rotational you have to choose. If you are taking the moment as a redundant force, then you have to choose the rotation. And if you are taking the reaction as a redundant force, so you have to take the displacement. You have to choose the vertical displacement. So here this is the rotational displacement. You have to choose, this is one coordinate 1 and this is your another coordinate at joint B. Because you are choosing MA and MB as a redundant force, so you have to take, this is the coordinate 1 and this is the coordinate 2. The bending moment diagram in release structure known free moment diagram, because you know, because here there you are having the uniform distributed load and here there you are having the point load. So due to this uniform distributed load and due to this point load, you must have to draw the bending moment diagram. Because you know, if there is your UDL, so what is the bending moment diagram? The bending moment diagram is your parabolic. And what is the maximum ordinate? What is the maximum ordinate? The maximum bending moment here, WL square by 8. So WL square by 8. So W is your 60 and L is your 4. So 60 into 4 square by 8. And here, so the point load you are having at the midpoint. So what is the maximum bending moment here? So WL by 4. 100 into 3 by 4. So you have to draw the bending moment diagram of the determinate structure. For AB, you have to draw the bending moment diagram. Then for BC, you have to draw the bending moment diagram of the release structure. So here WL square by 8, 120 kilonewton meter for AB. And the free moment diagram is a systemic triangle with maximum ordinate WL by 4. 100 into 3 by 4. So this is 75 kilonewton meter for BC. So this is for AB and this is for BC. So 120, here the bending moment, maximum bending moment, parabolic, and here triangular, and the maximum bending moment is 75. Then you know, in conjugate beam method, so how to find out the displacement? What is the bending moment value you got here? What is the loading of the conjugate beam method? So you have to take the M by I diagram is the loading of the conjugate beam method. So the conjugate beam for the release structure has two simply supported beam, A dash B dash and B dash C dash with M by EI diagram as load of the conjugate beam. So what is the bending moment you got? And that the bending moment by EI diagram is the loading for the conjugate beam. You know this is, and here also you know the bending moment here for this 75. So the M by EI diagram is the loading for the conjugate beam. Your objective is you have to find out what is the displacement at the coordinate 1, what is the displacement at the coordinate 1, and what is the displacement at the coordinate 2. So you know, in conjugate beam method, if you want to find out the displacement, that is the rotational displacement, because here you are taking the moment as a redundant force. So you have to find out the rotational displacement, rotation at A in AB. So when you find out the rotation at A in AB, in conjugate beam method, what you have to do? You have to find out the shear in conjugate beam at A dash. So what is the shear force at A dash in conjugate beam? So that will give the rotation at A in real beam. This is your real beam and this is your the conjugate beam. So you have to find out the displacement in real beam along the direction, along the coordinate direction 1. So what you have to do? So in conjugate beam, you have to find out the shear force. You have to find out shear force at A dash. This is the parabola. You can find out what is the shear here. Shear is equal to the reaction at A dash. You know that is shear in conjugate beam at A dash. You can find out because what is the total load you are acting here. So this total load divided by 2. Then you can find out what is the reaction here and what is the reaction here. What is the total load here? Because this is a parabolic. So here the total area of this diagram is your 2/3 into base into height, and half of this load will share by this reaction, and half of this load will share by this reaction. So R at dash is your equal to 160 by EI. This reaction is your equal to the shear at A dash. So this shear is your equal to the rotation at coordinate 1 due to the applied load in real beam. Similarly, you can find out the delta 2L. So what is the displacement at coordinate 2? You have to find out what is the displacement at coordinate 2. Here also similarly you can find out, so what is the reaction at B? What is the reaction at B? And that reaction is the shear at B. So that shear is your equal to the shear of the conjugate beam at B is your equal to the rotation of the real beam. So the rotation at B, delta 2L is your equal to rotation at B in AB plus rotation at B in BC, because here you have to take, this is the coordinate. So here you have to find out from this span what is the rotation, and from this span what is the rotation. From this conjugate beam you have to find out what is the reaction here, and from this side conjugate beam you have to find out what is the reaction here. The sum of the reaction is the total rotation, the displacement of the joint B. So here you have to find out what is the reaction here, and here you have to find out what is the reaction here. This two total reaction is equal to rotational displacement of this joint B. So rotation at B in AB plus rotation at B in BC. From AB you have to find out the rotation, and from BC span you have to find out the rotation. So in conjugate beam method, so what you have to find out, the shear at B dash in A dash B dash and shear at B dash in B dash C dash. So after getting this one, you know that this is the reaction here. So 2/3 base into height, this is 160 by EI. And then from this is triangle. So from triangle, you know what is the area of this one? Half into base into height, half into 3 into 75 by EI. So half of this load is equal to the reaction at B dash. So this is the displacement delta 2L. So this is, you got the displacement at coordinate 1 and 2 due to the applied load. Then the next step is you have to find out the displacement due to the redundant forces. So this is your alternative method that you can find out delta 1L and delta 2L. Then the next step is you have to find out the displacement due to the redundant forces. So what you have to do? So in this case, you have to apply unit force at coordinate 1. Then you have to apply unit force at coordinate 2. Remove all the load and only you have to apply the unit force, unit moment. So in this case, you have to apply the unit moment at coordinate A, because along the coordinate direction 1 you have to apply the unit moment, and along the coordinate direction 2 you have to apply the unit moment. So have to apply the unit moment along the coordinate direction 1. This is the figure. Then the resulting bending moment diagram with divided by EI value are shown in figure, loading for the conjugate beam. Then what you have to do? So after applying this 1 kilonewton meter, so then you have to plot the bending moment diagram. So this is the, if 1 kilonewton meter is the bending moment here, the ordinate of this moment is your 1 kilonewton meter, and here this side the moment is your equal to 0. So simply this is your triangle. Bending moment here is your 1, and this side is your 0, and here there is your no loading. Here there is your no bending moment diagram. So then after plotting this bending moment, then the bending moment by EI diagram is the loading for the conjugate beam, so M by EI. Bending moment is your 1, so 1 by EI is the loading for the conjugate beam. So for AB and for BC there is your no bending moment, so here the loading is your 0. So this is the conjugate. Similarly here you can find out, due to the unit force at the coordinate 1, find out what is the displacement at coordinate 1 and what is the displacement at coordinate 2. Due to unit force at coordinate 1, you have to find out what is the displacement at coordinate 1 and what is the displacement at coordinate 2. Since conjugate beam is a simply supported beam, delta 1 means the displacement at the coordinate 1 due to unit force at the coordinate 1. So rotation at A in AB, so you have to find out rotation at A in AB. This is your AB, this is your AB, real beam, and this is the conjugate beam. You have to find out delta 1. So delta 1 is equal to the shear force at A dash. So delta 1 is your equal to the rotation at A in AB is your equal to the shear at A dash in A dash B dash. So you can find out taking moment about B dash from B dash. So you can find out what is the reaction. RA dash into this distance is equal to half into base into height into the CG, the central distance, 2/3 into 4 from this end. So what is the moment? So because this side is your 1/3, this side is your 2/3, 2/3 into 4. After simplifying this one, so reaction at A dash RA dash is equal to 4 by EI. Taking moment about B, so RA dash into 4 is equal to this much, and RA dash is equal to 4 by EI. Delta 1 is equal to RA dash is equal to 4 by 3I. Similarly, find out what is the displacement at coordinate 2 due to unit force at the coordinate 1, delta 2-1. Because due to this unit force, you have to find out what is the displacement delta 1-1 and what is the displacement here 2, delta 2-1. Similarly, delta 2-1 is equal to rotation at B in AB is equal to shear at B in A dash B dash. So taking moment about this one, RB dash into 4 is equal to half into base into height into from this side L by 3. This 2 by 3. This is 1/3 L. So here this is your 1/3 L. Then RB dash is equal to 2 by 3 here. So due to the unit resultant force at the coordinate 1, so what is the displacement at the coordinate 1 and what is the displacement at the coordinate 2? Then what you have to do? Then you have to apply the unit force at the coordinate 2. You have to apply the unit force or a unit moment along the coordinate direction 2. This one. You have to apply unit force or a unit moment here. 1 kilonewton meter, and due to this unit force or unit moment, you have to find out what is the displacement at A and what is the displacement at B. So here you see delta 1-2 means that this is the displacement at 1 due to the unit force at the coordinate 2, and delta 2 meaning so the displacement at 2 due to unit force at the coordinate 2. You have to find out delta 1-2 and delta 2. Similarly, you can find out here, you see this is 1 kilonewton meter. So the ordinate is 1 kilonewton meter and here 0. So this is the bending moment diagram. And here this side also 1 kilonewton meter and this is the ordinate. So this is the bending moment diagram. This is the bending moment diagram. So the M by EI diagram is the loading for the conjugate beam. So M by EI. So here 1 by EI and this side 1 by EI. This is the loading for the conjugate beam. So you have to find out delta 1-2. And the delta 2-2. So delta 1-2, this is the displacement at 1 due to unit force at coordinate 2. So this is equal to rotation at A in AB, rotation at A in AB is equal to shear at A in A dash B dash. So similarly, you can find out what is the shear here, what is the reaction here. Similarly, you can that is by taking moment about this RA dash into 4. And this is half into 4 into 1 by EI, and this is the CG distance, this one. Then here also this is this one 2 by 3I, delta 1-2. Then similarly find out the delta 2-2. So delta 2-2 here due to from this side and from this side. So delta rotation at B in AB and rotation at B in BC. So shear at B dash in A dash B dash plus shear at B dash in B dash C dash. So this is the delta 2-2. Then by using the consistency conditions, the final displacement you know, here you see, so there is no displacement takes place at B and A. There is no displacement because these are fixed. So there is no displacement, and here also there is no displacement. From the consistent condition, the final displacement delta 1 0 is equal to 0 and delta 2 is equal to 0. So the matrix equation is your delta del P is equal to delta minus delta L. So here you see, so delta is the flexibility matrix. Here you got the flexibility matrix delta 1-1, delta 1-2, delta 2-1, and delta 2-2. This is the flexibility matrix. Then this is the force, the resultant forces P1, P2 at coordinate 1-2, and the final displacement is your 0-0, and this is the displacement due to the applied load. Then after simplifying this equation, you have to find out P1, P2. You have to take the inverse of this matrix, flexibility matrix. You have to take the inverse of this flexibility matrix. So after simplifying this matrix, then this is the simplification of the inverse matrix. then you find out what is the redundant force P1 and P2. So this is your the final P1 and P2 value. P1 is your the moment at A and P2 is the moment at B. MA is equal to P1 and MB is equal to P2. This is MA 85.87 negative means anti-clockwise direction, and this is also P2 is also this one 68.250. So after getting this moment, then you can plot the bending moment diagram. 85.8 this one 68.250, and here this is your 0. And due to loading, you know this is the bending moment diagram parabola, and this is your the triangle. Then the net bending moment is your, this is your negative, this is positive, this is negative and positive. So this is the final bending moment diagram. Now all are clear.